Hi, I wanted to have a go on the next problem today. When I first read it, it appeared to be rather trivial because I read it so points in the interior of each component, or two distinct components, and that appeared easy. Like if we have Z1 in alpha 1 minus first equals Z2 in the interior of F here. That means that alpha 1, alpha 1 Zn lies in the interior of F, and alpha 2 Z2 does as well. And this guy lies in gamma, so that's obviously impossible. But if we look at the fundamental domain of the full subgroup of level 2, gamma 2, then a point may actually lie here on the boundary between two components. And then what? So that's the problem. So this way I was only handling this was the trivial part. So now assume that Z1 lies in alpha j f to the minus first f and alpha j to the minus first f, two distinct components. And then isn't it obvious that the one it's equivalent to, it will be on in two different as well. You know, I made a logical mistake here, because we have these two, they are not equivalent. They must be equivalent with a guy in gamma mark. So what I did here was wrong. Now what did I write there? That should have been a Z1. So they are not equal. And that means alpha Z1 that means alpha 1 Z1 lies in the interior of F, and that is equal to alpha 1 alpha Z2 but alpha 2 Z2 lies in F0 as well, in the interior of F. Now, what can we conclude from that? So if you have 2 points in distinct components, alpha 1 this is Z1, of course. We must apply this, of course, too, that alpha 2 of Z2 lies in the interior of F. And alpha 1 Z1 lies in the interior of F. And then they must be equivalent. So if we call that U1 and U2, they lie in F0. And then we write Z8, Z1 like alpha. So, my God. It's really much more easy to do this when I work on my own paper. I'm sure you can see it by now, but I still don't see it. We'll just remove this line. U1 and U2, they both lie in the interior of F. So all we have to do is to make a connection between them. And A1 to minus first U1 equals Z1 equals alpha, Z2 equals Z2 That's alpha minus first, alpha 2 minus first of u2. So we get alpha 1 is equal to alpha 1, alpha 2 to minus first u2. This lies in gamma, and that means that u1 equals u2. Now we need to show that now we need to use that these are distinct, generate distinct cosets. Oh my God. Time for a break, guys. All right, I had time to look it over. Alpha 1 and alpha 2 are different generate different side classes, and alpha lies in gamma mark. And now U1 and U2 are points that are then gamma equivalent in the interior of the fundamental domain. Therefore, the 2 points are equal, and the mapping is the identity. And this is one side class of gamma mark. So when we multiply it with the inverse of another, it can never give unity. There should be unity, of course. The identity. So that was it. So now let's go to the other guy. So we have 2 points on the boundaries. Let's just put it on the boundary. Let's just call it it's not to minus first. So 2 points No, it is the inverse. So alpha I, alpha j, alpha k, alpha l to the minus first, and these two are distinct, generate distinct side classes, and these two do as well. So what can we conclude? Alpha I of z, alpha j of z1 lie on the boundary of f, as does alpha k z2, alpha l z2. That doesn't give so many possibilities, really, but they expand rapidly. Because this point may be lying here, and then here, here, or here. They could be this one hit more times, or any of these. So this is one group here, where the other is this, and one group here, where the other is this, and then one group where they are all the same. That's obviously impossible. Or this could even be the same point, couldn't it? Just, no, then it would map to two distinct points. So they have to be distinct. So that means that might be that and that might be that, or like here. And the same with this guy. And now Z1 and Z2 are equivalent in gamma mark. That's rather interesting, because if it's this, if they are here, then alpha must be S, and if they are here, then alpha must be T. And if they're here, they can only be mapped to each other by S, but then S lies in gamma mark, and the same here. If it's T, then T must be in gamma mark, so they are equivalent, and then they must obviously be on the boundary. So what we have here is that if it's like here and here, then T must lie in gamma mark. It doesn't, it's T squared, so we need to go out here before we get them. However, S does lie in there. No, it doesn't. It doesn't. I just missed that. S neither lies in. I just have to check. Yeah. It's generated by T squared, so T squared lies in it, and S doesn't, and T doesn't. So that seems that my argument is sound. Unfortunately, I'm not quite sure that it is totally sound. So I use the points that are mapped to each other on the boundary, and there are those points mapped by T, only possibility, or those points or pairs of points mapped by S. And that requires that it lies in gamma, so it couldn't be or could we hit that point using S? I do have a feeling that I haven't covered it precisely enough. Well, I can clearly conclude that I haven't made a precise argument, because then I wouldn't doubt. So I just need to think it over. I think it's right, but I'm not quite sure.